My name is Guillermo Cuerva, and today I'll be presenting my advances on my PhD thesis, which is turbulent characterization in Hall thrusters, with my advisors, which are Eduardo Edo and Miguel Pérez Encinar. These are the contents. So let's delve first on what is a Hall thruster. It's one of the well-established and mature technologies that we use in space operations due to this high impulse. And how does it work? Well, you have a backplate on your left, which has a potential difference between, which is called the anode, has a potential difference with an electron gun, which is called the cathode. And you inject a neutral gas in that anode, which interacts with the gun, with the electrons that are injected by the gun, which are magnetically confined, and you ionize the gas, and you accelerate those ions with that potential difference. Even though it's a well-established technology, there's still some open problems, mainly the anomalous electron transport and the plasma wall interactions. But what do we mean with anomalous electron transport? Okay, so if you think in a simplified model of an E cross B plasma, axial azimuthal, what you see, and you have a magnetic field that is pointing outwards in the plane, the electrons are gonna have a gyro motion around the magnetic field lines, and they're gonna move along those lines. They're gonna have a azimuthal drift in the E cross B direction due to the electric field and the magnetic field. And they're gonna also have an axial drift that at the beginning it was thought to be due to classical collisions, but after some observations, it's shown to be a much larger drift than expected, and therefore has to do with mainly azimuthal oscillations and plasma turbulence. So what are the goals of the thesis? Well, is to the theoretical study of main kinetic instabilities in a Hall thruster, and mainly contributing to three questions. What are the main instability modes triggering the plasma turbulence in Hall effect thrusters? Develop reliable and computationally feasible numerical models of this plasma discharge, and from that, how we can extrapolate those findings into a simplified turbulent models for a Hall thruster. So, and this thesis based upon on the work previously established by Alberto and Enrique, which I owe them a lot. So right now, what happens in the PhD in my thesis is that I have two simultaneous paths. The first one, which is the one that I'm gonna explain really briefly, is the improvements of the Picasso peak code in its axial azimuthal version, because it lacks some important physics, mainly the plasma wall interactions and a simplified neutral treatment. So the idea is to include those plasma wall interactions and see how it affects the model. Briefly, introduction on the peak. What you try to do is that you try to solve, instead of solving the Boltzmann equation, what you solve is the movement of the macro particle. You populate your domain with macro particles, and you move them with an external magnetic field and an electric field given by the Poisson equation. You also have a collisional parameter, which is usually done by MCC. We cheat in Picasso a little bit, because what we do is we augment the vacuum permittivity a little bit in order to ease up the numerical constraints, and I tell you this for the next steps. So how do we introduce wall effects on an axial, here in an axial simulation or in both axial and azimuthal? So at the wall and in the plume of the Hall thruster, you have ion recombination, you have collection and emission of electrons, and you have plume divergence, and you have dielectric walls, so the current at the walls is zero. So the idea is to capture this phenomena with a simplified model that moves the particles radially with an analytical expression, and remove and emit particles to ensure that you have wall-free, current-free walls. And also includes plume divergence. And we did a study, a bibliographic study, to overcome the previous limitations from those attempts to model those plasma wall interactions. I present this on an IPC paper. I'm not going to go through it, but the idea is that in these profiles, you see similar things, or very similar profiles as what Alberto sees on its axial radial simulations, where Picasso is actually solving the radial direction. And these axial profile, wall profiles, the electron BDFs, they resemble what you see on an actual axial radial peak simulation. We also compare with in the axial peak, we try to compare with the 1D fluid model, because there's mainly difference between the kinetic results and fluid results, mainly because of the assumption that fluid has that kinetic does not. Also, the fluid model 1D from Davide Poli in the quasi-neutral one has a empirical collision parameter, which depends on the temperature of the electrons. And when you compute that wall parameter in the peak, you see, which is the, I don't know, well, is the one what is the, here, is this graph here. You see that the wall parameter for the peak is way bigger compared to the constant, is bigger and evolves actually compared to the constant value of the fluid, as well as the energy of the impact of the electrons to the wall in the fluid follows a 2T trend, which is this plot over here, whereas in the peak is a more complex phenomenon. So this is a good thing because you can see the difference between peak and fluid, as well as, but you also see that the profiles are more or less similar, except for the peak of the temperature, but for example, the discharge current is quite similar. Now, the second part, which is the funny part, is the GPU-based kinetic simulations of all thrusters. So Picasso has some disadvantages, mainly due to its parallelization. We are limited to only 40 threads, and also what I talked about that we're cheating. What happens is that since we ease the numerical constraints, this can affect the growth and saturation of instabilities. So actually, we maybe not be seeing what is actually happening on a whole thruster. So the idea was to use GPUs to develop a new axial azimuthal peak code to study simplified whole thruster scenarios without that scaling in order to see what happens really. So what are the limitations? Well, in a peak code, you need to resolve electron dynamics, so their length scales and time scales, and you also must also resolve the length scales and the time scales of the Hall effect thruster, which are way bigger in magnitude, way bigger. And Picasso does that by doing an artificial scaling, which can modify the onset of instabilities. It has been proven by bibliography. So why do we use GPUs? Well, it allows for massively parallelization, up to 10 or 100 times faster than CPU-based codes. You don't need the artificial scaling. You can have more particles per cell, which improves the accuracy. And you can have high resolution and long time simulations. And also support parametric studies because you are doing the simulations way quicker. So this is a simulation, one of the first ones that we did on the GPU, which is really nice because this is no artificial scaling. This is an azimuthal instability, and this has a case which is what is called the benchmark to the axial azimuthal case, which is a simple where here you can see the oscillations of the electric azimuthal instabilities, and the anomalous force will be just the product of the density times that electric field. The anomalous force does move the electrons actually. Why this is important? Well, this case is important because it's like it's a simulation case that most of the plasma community has done, especially in peak, and it focuses on capturing key kinetic effects on the whole thruster and is benchmarked by multiple peak codes. And the idea is that the GPU was able to match what the results, as well as so these are the results from the published results, and these are the results from the GPU, which are pretty nice. And also a good thing is that the GPU is way faster than any of those other codes, in the sense that the Picasso G, I'm really bad with names, but Picasso G, it has done this simulation in 188 days, whereas the best code on that article lasts in 2.5. And this is a last article trying to do the same thing, which does it in 1.8 days, but the difference is that the GPU is way bigger. Well, it's not way bigger, but it's better than the one that we have right now. So this is really nice results, although it's not nothing new, but it's important to benchmark it in order to future simulations, which is the important thing now. So what happened? The benchmark has a lot of limitations, mainly that it's highly dependent on the ionization zone profile, you have a low magnetic field, and since you have many things at play, they don't really delve on what happens with the instabilities. They don't talk about the growth, they don't talk about the saturation. So the idea is to focus on in the acceleration region of the Hall effect thruster and try to find a simplified scenario where we can control what happens with the instabilities, how they grow, how they saturate, and that's what we're working on right now. So far, we have obtained axial profiles which follow the trends that you would see on a Hall effect thruster, but there's no instabilities, or I will show them to you, but they're not. But the good thing is that it's a strong baseline for iterating and obtaining a realistic scenario or a simplified scenario with instabilities that appear and we can study it more easily. So the summary and current future work. So for the axis improvements on Picasso, we implement a simplified model for plasma wall interactions, which is capable of dielectric walls, have secondary electron emission, plume divergence, and the idea is to include this model on axial azimuthal simulations of the Hall thruster of Picasso. And we also want to develop in the future a fluid model for the neutral dynamics, because right now it's a very simplified model. Then for the GPU-based kinetic simulations, we have benchmarked this code, and we are the best. And the idea is now go to simulations that are better to understanding what is going on with the instabilities in a Hall thruster, because it's a very rich, and as Mateo explained, very rich and very complex scenario. So the conferences that I attend were last year IPC, and the next year, this next year in IPC, which we'll try to see if the simulations of the GPU show some light, and then we are preparing a manuscript on the axial peak simulation. So thank you very much.